take a mic.
My question is for Professor Steve Gray and Professor Zhang Xinlong. I heard you all talk about a new specialized helium low discharge source being used for the ambient ionization method. And I also noticed Zhang's group also developed a low temperature plasma absorption ambient ionization method. I want to ask you, both of you, to comment on these two methods in terms of similarities and differences, in terms of ambient performances, pros and cons.
Definitely, we can answer this question because one of my students also worked in his laboratory for DBD, the low temperature plasma. So he knows much better than me because I didn't do the work like him.
You're probably going to get two different answers, actually, depending on who you ask. So if I don't come up with an accurate result, you can hit me yourself. Give me a high sign. Generally speaking, the direct current helium, what we call FAPA, which is ambient pressure low discharge, creates a hotter gas temperature plume. That is to say, the flowing afterglow that comes out of the source has a temperature of about 230 degrees Celsius. And it also seems to have a relatively high abundance of high energy helium species. These helium species we know to be important in the creation of the charged water clusters as well as charge exchange reagents. Now, what we tend to run the discharge at about 500 volts and maybe as high as 100 milliamps. So the amount of current that's moving to the discharge from the FAPA source is much higher, and as a consequence, we get what we find to be a higher density of these reagent ions. And that means in the end, one of the matrix effects with API sources that, or APCI sources that everybody knows is this competitive ionization mechanism, where if you have a high abundance of something that's easily ionized, it'll tend to suppress signals from those species that are less easily ionized. And that tends to be less of an effect with the FAPA source. Let's move over to the dielectric barrier discharge. Here you have a source that is capacitively coupled, and it tends to create a lower temperature gas stream. But what we find is that we have a really interesting high abundance of really high energy helium species. So it seems to us that with the LTP, what he calls the LTP, or what we sometimes call a dielectric, modified dielectric barrier. DBD, thank you. With a DBD, we tend to see a high abundance of these helium species, and that's disproportionate to the population of other things. That is to say, it's a really efficient way of creating the helium metastable, but the gas temperature is lower. So you have a lower density of reagent ions, but you also have the effect that there's a different desorption mechanism with the DVD as opposed to the FAPA source. And that has to do with the gas temperature. So there are advantages and disadvantages. We tend to see that the population of molecular parent molecules that are created are very similar. We tend to see that the FAPA has a longer linear dynamic range than the LTP. And we tend to see in our case at least that it has a little higher sensitivity. Would you agree with all of these statements?
Yeah.
Anything to add?
I would like to also say something in Chinese because probably some Chinese can understand what he said. Okay. Just give a very simply explanation about it. 我简单用这个中文解释一下，就是刚才问的这个问题是这样，就是瑞他们实验室呀，现在用的是辉光放电。我的实验室呢用的是就是叫 DBD， 就是介质阻挡放电。这两个放电的本质区别有点像什么呢？我举一个形象的例子，因为大家在座的大家都对原子光谱比较熟悉。你们在仪器分析教材里头呀，有一个就是辉光就是那个电弧放电的时候啊，这个咱们教材上说有一个直流电弧，有一个交流电弧。所以如果是直流电弧的话呢，我们要把两个碳电极碰到一起。然后呢，一点火就有点像电焊工那样点一下，然后呢，它先短路一下，然后再拉开。所以你刚才看它的那个录像上啊，就把两个电极啊先碰一下，然后再拉开。 交流放电的好处是它可以自己点火，这是第一个。第二个呢就是温度，这个直流放电一般温度非常高，所以它刚才介绍呢就是温度是很高的。但是呢 DPD 放电呢它是一个 low temperature 的，就是说是个低温度的这个放电。所以这两个放电呢有一点不太一样的地方，比如说我们最近在德国应用化学上发的一篇文章，就是我们可以做字画上，比如说纸上头的这个印章的成像。那么这样如果要是用直流放电的话就很难，可能一放你就把纸就烧掉了。所以这是这两个的区别。当然温度高有温度高的好处，温度高呢这个原子化的效率、离子化的效率可能会高，但是温度低有温度低的好处，它比较容易点火，而且它比较温和，特别是做有机质谱的时候，它是个这个软离子源，所以我大概解释 OK。
I agree.
Gentlemen, thank you so much. Oh, you are getting the busy guy now. Microphone.
Yeah, just for the question also focus on image distribution. If the sample is not flat, do you need do some sample preparation? And also if the sample the sample shape is not irregular,
That is a really good question, and I don't have a good answer for it.
That was a quick answer, so you got the prize. So,
I have a question. I'm very interested in direct solid analysis by FAS. And want to know how about the limitation of sample volume. You know, if you use this technique, the sample volume is very small. If increase the sample volume, I guess some problems.
In fact, for the sample volume, it could be from sub-milligram to 50 milligram. So usually for one measurement, the sample quantity is already big enough for the representation of your sample's characters. 它的这个问题呢，是说机械固体晶样的晶样量，那么通常比较小，那么有没有办法呢，说把这个晶样量增大一些？其实，在机械固体晶样石墨钴里面呢，一般晶样量是从0.几毫克，那么到最大可以到50毫克，那么最终的这个它的量的一个极限呢，就是说那个石墨管里面它有个石墨周，就说你不能超过那个石墨周的那个平的那个挡光，不能挡光的样品量。但是一般来说，有几十毫克的样品量，它的这个代表性非常好。那么大量的实验里面呢，一般是用0.几毫克到几毫克的这个样品量。那么大量实验证明呢，这样一个样品量还是非常有代表性的。只要你的样品不是说特别不均匀的样品，应该都没有问题。Yes.
So if the sample is particle, is it possible? For example, alloy sample.
Yes, it's no problem. It doesn't matter whenever what's the shape of the sample. It could be a particle, it could be a seed, it could be also a powder. Whenever the sample can represent your real sample's concentration.
But if for alloy sample, I think it's difficult to.
You don't. Of course, it cannot be so big, but you know the quantity is only lower than 50 milligram. So the size of the particle were not so big, but inside of the furnace, the higher temperature is more than 2,500 degrees. This is already high enough to destroy any of alloy.
So you mean if the sample, for some alloy sample, the particle is big or?
If it's big, you need to part it. Yeah. Anyway. The highest quantity, the weight of sample cannot be more than 50 milligram. So in such a weight, usually size is very small.
ladies and gentlemen, give all my speakers a big hand.